Uh-oh. All right, I think we're back. Do you want to confirm on the live? All right. Again, it's moving. Okay, we're back. I super duper 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 apologize about that. Again, uh made I'm on my personal computer now to get an actual functioning device. Okay. Sorry. So, back to where we were. So the whole point of what I was trying to show is, again, right, we were looking at our change in internal energy. And so again, we said basically we can summarize our enthalpy as our energy, which again, this energy is Q, so heat going in and out, plus again, whatever work is performed by the pressure volume, if you have pressure volume work. But then what you'll find is many of the situations that we look at, right, we're not doing pressure volume expansion, so our change in enthalpy will just mainly be focused on Q there. But we will, like I said, or what I was trying to say before my poor school computer crash, is that we will look at a few changes, right, where this is not the same. And so you would only get a difference, right, when you produce or use large quantities of gas. But like I said, we will have a practice problem for that. All right, so then, again, we had said that our enthalpy is not path dependent, so it's a state function. And this gives us several tricks, which you'll be able to use in our lab today. So enthalpy is always associated with a particular reaction. And so that means that this also reflects the amount stoichiometrically. So meaning, right, if we reverse it, the change in enthalpy flips. And you kind of saw that, right, with the CO, the carbon plus oxygen gives us CO2, right? Same process, we can just flip them, and that changes our sign. So we can do that. We can double it, right? Or we can do it, scale it by however amount. So again, in lab today, you're going to do a very small amount of molar amount of material, and again, calculate some enthalpies. And so it's an extensive physical property. Again, it depends on the molar amount. And so again, when our reaction is multiplied by a certain factor, then our change in enthalpy is also multiplied by that same factor. And that makes sense, right? So you're doing, again, this combustion reaction. So if we're looking at 1 mole, this is negative 393.5 kilojoules. And again, right, this is given for this equation. So that's 1 mole of carbon and 1 mole of oxygen in that. And then we can double it by 2. And so, right, everything doubles. And that, again, also means your enthalpy doubles. So now releasing double the amount of heat, which, again, right, makes sense kind of physically what you know, right? Kind of you burn more material, and obviously it's going to make more heat. And again, like we mentioned previously, so this is going to follow mathematically. So you flip the direction, and then our sign is changed. So again, the dissociation of CO2 back to carbon and oxygen is positive then. So these will be good principles. And so then this also means that we can write any reaction as the sum of formation reactions, or reverse. And okay, so let's look at what this means. And so we'll look at this. So we have our change in enthalpy of our reactions, and then this is, right, our formula, but we'll break this down and write summation. So we want to take the sum of our standard heat of formation, and we'll look at where to get this value and what that means, minus our standard heat of formation of all our reactants, and then that gives us, again, the overall change in enthalpy for our reaction. And then, again, it does scale by molar amounts. So N would be our coefficient. So right, we start with our balanced equation and then figure out, again, the standard enthalpies for each product and then multiply it by the correct molar amount. All right, so then that brings us to, well, what is our standard enthalpy? And so now we're just, again, setting up kind of the conditions for this. So we have our standard conditions and standard enthalpy of formation. And so, right, this is your table that's probably in the back of the book somewhere, or you can, right, Google this anywhere, standard enthalpies of formation, and you'll get plenty of tables. And so this is defined, right? So it's at a certain set of conditions. And so you kind of notice that a lot of these, right, are just at kind of ambient conditions. And so that means that our gas is at 1 atm of pressure. Our solids and liquids, again, are going to be kind of at their stable ambient form. So 1 atm of pressure, 25 degrees Celsius. And then if we were talking about solutions, 1 molar solutions. And so we have, right, our standard enthalpy change then is when all these reactants and products are in their standard states. And we'll look at, again, what that means. And then our standard enthalpy of formation then is the enthalpy change of our reaction for forming 1 mole of pure compound from its constituent elements. So again, we'll see what that means exactly. And so let's kind of first orient ourselves with our table and look at a few things. And so notice that things are in their elemental form, aka, right, how they're found just in ambient temperatures, conditions, pressures. That's going to be 0, right? So like bromine in its liquid form is 0 versus bromine gas, right? So implying energy was added to get it into a different state. So that's interesting. So kind of pay attention to that. You have graphite. So notice that has a 0 heat of formation. Calcium, again, 0, right? Anything in the elemental form. So H2 in its elemental form is 0. And again, just kind of taking it in. So sometimes it does depend on the shape. So, right, some subtleties there on the exact crystal structure. So that's what accounts for some differences. All right, so let's try this first step. And so what it wants us to do is, again, right, we want to figure out what's the change in enthalpy for this reaction. So ammonia plus oxygen to give us NO and 6 equivalents of water. So see if you can start to do that. So we have our table here, or if you have your book, you should have a similar table. And so that's the other thing, is when you look up these standard enthalpies of formation, double check your units. So generally it should be in kilojoules per mole, and that's kind of the standard that we've been using, right? Either joules or kilojoules. But you might see electron volts or anything else, right? So, or kcals is the other common one. So just be aware of that. And so if you look up a different chart, don't be shocked if you see a different value, if it's a different unit. So just keep that in mind, right? And so now let's try to do that. So again, hunt for the values of ammonia, oxygen, right, NO, water. Pay attention to the states, right? Because we saw that that could make a difference. And so see if you can do that. And remember, it's products minus reactants. Oh my gosh. Okay, let's see. So it should be on there. But yeah, oxygen is one of those ones that you could recognize it was in its elemental form, but yeah, let's start kind of seeing what y'all found. So we have oxygen at 0 for standard heat of formation. Did we get ammonia? What do we find for that one? So negative 45.9, so right there on the chart and right correct state, so that looks good. And then NO, so it looks like it's 91.3, again in our gas state. And then water, what do we find for that one? Oh, and then, so double check that one, because that's the liquid form, right? But it's the gas, yeah. So negative 241.8. All right, so that looks good. And then just glancing at our formula, so remember we have to multiply it by the correct molar amount from our balanced equation. So now I'm going to start plugging all that into the calculator. And then it's going to go products minus reactants. So I'll start with that. Let me clear this. So negative 241.8. Oops. I go times 6. Again, since we have 6 from our balanced equation. And then plus our... So I'm going to just write that down for a second. So our products come out to negative 1085.6. And then now I'm going to sum my reactants so I don't mess up my algebra here. So then negative 45.9 times 4. And again, now we're going to go products minus reactants. So minus our negative here. And so then I get an overall change in enthalpy of negative 902. That'd be kilojoules for this process. Did we all get that? Oh, negative, sorry. Didn't get it, but getting there. So yeah, just watch your signs on those. That's really the trickiest part, is the signs. And then again, we have to think about what we just said. So this is for this reaction. So we're saying, right, the combustion of 4 equivalents of ammonia releases 902 kilojoules of heat. And you could also think about scaling it, right, with respect to the ammonia or anything else, right? So again, you could scale accordingly. Like if you were asked the molar amount for one mole of ammonia, what would that be, right? You divide it by 4. And again, just a reminder that the enthalpy is an extensive property. Again, it makes sense, right? If you're a pyro, then you know the more stuff you burn, the more heat, which is also the danger of kind of those large bonfires too, right? So again, more heat, and so the more reactants, obviously the larger the enthalpy. Oh, we lost our arrow here. And so again, right, we're given our amount that's dependent on this equivalence. So we're looking at 1 mole of propane is combusted with 5 equivalents of oxygen to give us 3 of CO2, 4 of water. And so the change in enthalpy of this reaction is negative 2044. So again, it's releasing 2044 kilojoules of heat. And so now let's figure out, oh man, I had a cute meme that now I have to re-find. Because we can't talk about propane without doing a Hank Hill meme or something. So see if you can figure this out while I get a new meme picture. That's like the one thing I did prep today. No, I'm joking. So we're looking at a propane tank in our home barbecue, has 13.2 kilograms of propane. And so calculate the heat and kilojoules associated with the complete combustion of all the propane. And again, you're given what 1 mole amount releases. So how might you figure this out? So again, I'll give you a minute or two to get started. So how are we doing on this one, or what do we need to solve? Excellent, right? So that's all we need to know. That's really the missing piece. So, right, we're given what 1 mole is. So let's figure out how many moles we have in here. So I'll just first of all convert to grams. And then does anybody have the molecular weight of propane handy? 44.097 grams per mole. I like it. And so now we can just divide and figure out, again, how many moles we have now. So 13, 20, divided by 44. And so about 300 moles roughly, or 299 moles of propane. And so now we can just multiply it, right? So again, we were given what 1 mole releases. And so now we can multiply it by that same amount. And so now we would expect, and that's kilojoules, so, and we have 3 sig figs, so we can round it to 612,000 kilojoules roughly there. And then, right, watch your signs, but also understand what it means, right? Again, if it's negative, we're talking about heat being released, so it's going to feel hot. So I'm not so much a stickler about the sign if you were to say, right, that heat was released. As long as I'm as long as I can tell that you're understanding which way the heat is flowing, since, you know, sometimes the signs can get confusing too. But questions on that one? So yeah, fairly straightforward so far. All right, so now we'll look at our small issues. So like we said, most of the time we're going to be looking at our system where we're mainly just focusing on the enthalpy of our reaction being related to Q. Again, we're just focusing on the heat being exchanged, so whether something is strictly endothermic or exothermic. But we should still understand how to calculate our internal energy. Like I said, I don't think we'll see too many of these calculations, but we should go through them. And so like we'd mentioned, if we have a change in volume, then that means there's going to be some sort of work performed. And so we're also given this. So like I said, we haven't done gas laws formally yet, but we can accept that this formula exists. So this is our kind of PV equals nRT formula, but then it's just slightly modified to figure out, again, how much gas was lost, and then converting that. So like I said, we'll cover this later, but right now we're using this form, and we're using R, that's energy R. So different gas constant for different applications. So again, if we care about energy, we need to use a constant associated with energy. All right, so now let's kind of look at this problem. And so we want to see kind of what our error is. And so let's go through this. And so we're looking at, again, our combustion reaction. So this is one of our balloon demos. So again, kind of a good you can kind of imagine what happened again. And so stoichiometrically, you react 2 equivalents of hydrogen with 1 equivalent of oxygen to give us 2 equivalents of liquid water there. And so we have our change in enthalpy as negative 571.6 kilojoules per mole. And so now let's calculate, right, our pressure volume work though. And so let's look at this. So let's calculate. So what's our change in volume of gas? So first, let's look at our equation. And so it asks us to take the difference, so the sum of the stoichiometric coefficients of the gaseous product. So looking at this equation, do we have any gaseous product here? So no, right? And so this was good. So again, liquid form here, so kind of tricky what we're looking at. So yeah, we're losing a volume of gas. And again, thinking back to the demo, like that's part of what's going on is you have all this gas and then boom, it pops, right? And part of like what you feel is that change in volume. So let's work on quantifying that. Okay, so we had 0 minus, and then how many molar equivalents of gas do we have initially? Yep, 3. So good. So we have 0 minus 3. So we're saying that our change and essentially our stoichiometric volume is we're losing negative 3, right? So negative 3 moles of gas. And so now let's quantify that. So again, we're saying that our pressure volume work is then equal to this. So pressure volume. So again, trying to quantify our work here is equal to, so negative 3. Then, like I said, we need to use the appropriate R for energy. So 8.3145. Notice it's in joules, so just keep that in mind. And then times our temperature that we're at. And let's see. So probably just assume 298 since we weren't given anything else. So Again, standard temperature and pressure there. And so now let's look at this. So -3 times 8.3145 times 298. And so then that gives us, so -7,000 joules, which is only -7.4 kilojoules, right? And so now we can kind of see like why we generally don't care about it and we don't generally address it. And so again, right, most properly, our true internal energy is equal to our delta enthalpy of our reaction plus our pressure volume work. And so, right, truly, kind of the corrected answer then would be, so we can take what we found our change in enthalpy to be, right? So that's fine. You can calculate this too mathematically, right? Just like we did before. You look at your standard enthalpies, so products minus reactants to give us that. And so then we have, so -571.6, and then minus. And so again, we decrease, so that means work is going to be done on the system. So minus a minus 2. And so then we get, right, a fairly small error, so -5,640, or excuse me, 564.2 kilojoules. Sorry, I can't speak. And then we could calculate, right, our percent error from this. And so then we can take 564.2 minus our 571. So we could calculate our percent error in that. So let's see. And I'm sure you guys can already tell it's going to be pretty low. And now convert it to a percentage. So about a 1.3% error, right, if we do not do that proper calculation. And so all that's telling us, right, is it's pretty negligible, right, accounting for this pressure volume work. And so again, unless you were doing like a really, really large quantity where maybe it would matter, or again, if you really cared about that small part here, then you might want to factor that in. But like I said, in general, we're not even going to worry about that and it won't come up in our problems, but it is pretty small compared to, right, the large change in enthalpy. All right, so then kind of more fun things about Hess's law, and this is totally the key to the lab as well. And so again, we're kind of thinking about things being path dependent, but like we said, this is not path dependent. And so what we're saying is, okay, well, we can take a reaction then, and we can express it as a different series of steps. And then we could calculate the change in heat for each one of those steps, and then sum it up, and it would be the sum of that. And so this is just kind of visually, right, what they said. So again, it doesn't matter how we got A plus 2B gives us D here, right? So we go to C. And so you could, like I said, quantify this, right? A plus 2B gives you C, and then C back down to 2D, and add up, right, every single one of those processes to give you your overall enthalpy. And it'll make more sense once we kind of do it. So let's practice this now. And so this is kind of a puzzle too. So you kind of have to play with it, right? Kind of guess and check. And so now let's look at our objective here. And so we want to get basically our standard heat of formation, right? So we're saying what does it mean? What's our standard heat of formation to get propane? And so if we go back, let's look at the definition, just so we're all on the same page. So again, it says the standard enthalpy of formation is the enthalpy change for 1 mole of pure compound from its constituent elements. So that's what we're calculating or attempting to calculate here. So, right, we want to know what's our heat of formation for propane from our constituent elements. And so sometimes this doesn't make sense. And so I don't think that you could physically do this necessarily, right? So this is just kind of the mathematical part of just if we take carbon and hydrogen and then we make propane. And so we can't get there directly, so that's kind of the problem. And again, let's just make sure we know how to do this. So again, propane has 3 carbons, so that means I'm going to pick 3 carbons. Then we have 8 hydrogen total. And again, right, just get elemental hydrogen. Then we're going to need 4 equivalents to get to 8. So that's how we got there, right? So it's nothing tricky. Now the problem is, like we said, we maybe can't do that reaction physically. It just doesn't work out, right, combusting it. But these series of reactions we can do and we have data for. And again, this is what you're going to be doing in lab today. So we'll have our goal of what we want to figure out the enthalpy for. So it's going to be for the combustion of magnesium to magnesium oxide. So obviously we can't measure that combustion directly, right? That's pretty exothermic. You guys have seen that. But we'll break it down into its steps. So same thing. So we can break this down. So we have the combustion of propane. So propane plus oxygen gives us CO2 and water, and we have that. Then we have carbon plus oxygen, and that combustion gives us CO2. We have a value. And then we have H2 and oxygen giving us hydrogen or water in the gaseous state, and again we have a value for that. So try to puzzle out for a second. Like I said, this could be difficult to do initially, but what you're trying to do is flip these equations such that they add up to give you this expression. So my hint would be like maybe start flipping things like propane, it's on the reactant over here. I might flip this whole equation since we need it on the products and kind of go from there, right? Kind of flipping things appropriately, putting the elements that you need on the right side, and then see if you can add them up. But start to play with it and then we'll go over it. How is this one coming? What are some ideas? How should we manipulate these equations? Okay, so yeah, let's start with that. So I'll just rewrite it. So 3CO2 plus 4H2O gives us 5O2 and propane. All right, so then what else could we do? Well, you're trying to add them all together, but then like, so how many equivalents do we need to add? Let's just start with the second one, right? So how many CO2s do you have here? And yeah, so that's what we're getting at. So times 3, so now I'll rewrite that. And what we should also be keeping track of is our enthalpies, which I did a bad job initially. So the first one, I want to keep track that we flipped it. So now that's positive 2043 kilojoules. And so now I'm just rewriting our second equation times 3. So 3 equivalents of carbon plus 3 equivalents of oxygen give us 3 of CO2. And then we're going to have to multiply the 393 times 3 as well. And then just start double checking that things cancel out. So right, the CO2s are going to cancel out, so that's a good sign. And then, so let's kind of keep going. And so I'm just looking at my equation. So I have 2 equivalents of hydrogen here, but I need 4. So maybe I would probably just start by doing 2 and then writing it and seeing where we're at. So 4H2 then plus 2O2 gives us 4 equivalents of water. And again, don't forget to multiply by 2 now. And so now let's double check that we can add this equation and then it does give us what we're looking for. Why? There we go. Change my pen color here for a second. Well, that doesn't look like my pen. All right, so now just double checking. So let's see. 4 waters cancels. That's a good sign. So then I have 3 plus 2, so 5 oxygen on the reactant side, 5 on the products. So again, whatever's the same on the reactants and products, you can cancel out. And then it does indeed give us, right, what we're looking for. So just kind of looking at what's remaining. So 3 carbons plus 4 hydrogens gives us 1 equivalent of propane. And now we can add this up. So let's finish up this calculation. And again, just keep track of what we did. So now we have 2043, and again, it's positive, right, because we flipped it. So flip the equation, flip the sign. And now plus negative 393.5 times 3, because again, we multiplied it by 3, plus 2 times negative 483.6. And so now we should have an overall change in enthalpy for this of negative 104.7 kilojoules. And so again, that's also our standard heat of formation for propane. And so on an exam, this could have also been worded, find the standard enthalpy of formation for propane, and maybe this equation would not have been given to you, but merely just the series. So just thinking about other ways to ask that. So I'll add that. So find standard enthalpy of formation of propane. So again, that would be another way to word that question, and then the equation would probably not be provided, but instead you could come up with that yourself, though. Yeah. This? Oh, yeah, the 2O2, yeah, because we had 3 equivalents of oxygen plus 2 from here, multiplying it by 2. And then that gave us 5 overall, so then we could cancel out the 5 from up there from this combustion. Other questions? So again, right, this isn't necessarily an easy process, so expect to kind of guess and check, right, play around with chemistry. So I don't expect you to just like look at it and know it, right? You will have to kind of mess around with it. So get your scratch paper out, get your pencil out. That's my best advice for this topic. All right, let's keep going. We're kind of flying through that chapter, but that's fine. So we can do review on Thursday. Plus, I want to do a fun demo for y'all. All right, so like we said, so now we're just kind of going over that again. So again, it's reminding us what the standard enthalpy of formation means. We already saw these sets of condition, but I just kind of listed them again. So we're, again, all on the same page. And so we're finding that. So again, right, just a wording of our question. When we're asked to do the standard enthalpy of formation, you pull things out in their elemental forms. And again, like we saw from our chart, anything in its pure element in its standard state. So again, right, just standard temperature pressure is going to have a 0. But you can look that up on a chart, right? So you don't have to remember that. And so now let's try to do this problem. So this just wants us to write our standard enthalpy of formation for magnesium carbonate and then a sugar here. So we're just writing it. So right, what would that look like? We're not calculating it right now. We just practice writing it. So do we have our equations? Are we still writing it? Also watching the chat. I don't know if the chat left after our stream issues. So let's try A for a second, and then maybe I'll give a little more time for B. But okay, so we're trying to get to magnesium carbonate. And so what should our equation be? So just pulling out our elements. So what do we think? Yeah. Why two though? Oh, I'd probably just do like half oxygens. Yeah, but let's go with what you're saying and then we'll fix it. So yeah, you said 2 magnesium plus what? And so that gives us 2 equivalents though, right? And so again, when we're writing this, we want it to be for 1 molar equivalent. And so this is confusing, and this is a good example, right? So you have this odd number of oxygen. So you have 3 here, but obviously oxygen is a diatomic. But it's best practice now, because again, we want this to be 1 mole. And so that means we should scale everything accordingly. And so in this case, it's okay to use fractional coefficients for balancing. So we can do 3/2 equivalents of O2, and that gives us the 3 that we need there. So it's a little tricky. And so I'll give people another minute or so for B. Again, just kind of repeat that process. Do it for 1 molar equivalents of our sugar here. And trying to get papers. All right, so let's look at what we got for this one. So again, 1 molar amount. And so what should our formula be then? Somebody give it to me. Yeah. That looks good. Any questions on this one? Did we all get that? And again, scaling appropriately, diatomics, all those good things. So all that looks good. Questions on this? So yeah, definitely expect questions like this on your exam, either writing these equations for the standard enthalpies of formation or calculating them. So there'll certainly be some unknown adding equation. All right, let's keep going. And so like we kind of teased at the beginning, so the other way that we can quantify our energies is within the bond itself. And so of course chemical reactions involve breaking or making new bonds to create our product. Oh, we're almost out of time too. And so we can also use our enthalpy, and so we can figure out the enthalpy then of our reaction by comparing our cost of breaking old bonds to the income from making new bonds. And so the important thing to kind of note is that all these bond energies are kind of average, and so how we get them is that they're in the gas state, and then this assumes homolytic cleavage, which is true for the majority of the case. But let's, like I said, we're almost out of time, so this is a good place anyways to at least go over the definition of homolytic versus heterolytic. And so homolytic just implies that each atom contributes one electron. And so let's just look at a CH bond, right? And so the rest of this doesn't really matter. So just focusing on the CH here. So homolytic cleavage, we can write with this single-headed arrow implying movement of one electron. And so that means it's going to break, again, evenly, like so. And so again, this is how most bonds form, right? We've been looking at kind of, this would also be defined as maybe a normal bond is another term. Yeah, I mean, I'm kind of like shitty at it. but they're supposed to be like little half arrows, yeah. And then if we compare that to heterolytic cleavage, so let's look at a good example of a classic heterolytic cleavage compound. And so you can have, well, these are quite fascinating complexes, but basically they're known as frustrated Lewis pairs for acid-base reasons, which we're not there in the course. But what you can tell, so let's kind of back up before we look at how this bond is made. So this is not a normal bond. So this is what is known as a dative bond, meaning one atom is contributing 2 electrons to this. And so this is where our Lewis dot structures are really powerful. And so we can rewrite ammonia like so. And so we notice it has these 2 electrons that are kind of primed for bonding. And so that's what's going on in this case, is that nitrogen is donating those 2 electrons, right, to boron. And that makes sense. So just thinking back to boron, so boron only has 3 valence electrons. And so it's quite okay for it to be like this. And so notice, so that would only have 6 valence electrons, formally deficient, right? But this is why boron, why there's a lot of hot research right now with boron, because it can do cool things like this. And so since it technically is missing electrons, right, it is happy to accept those 2 from nitrogen, but then this would be a weird scenario where this would not be described by homolytic cleavage, right? So now when you cleave it in the gas state, so gas state cleavage then, and it would break heterolytically such that boron would get none of those electrons, and then nitrogen would get those 2 back. But like I mentioned, that's a weird bonding scenario, so we don't really see that, and you generally see it with these like nitrogen boron type of adducts or other sorts of analogous structures. But otherwise, when we're examining kind of our bond energies, we're just looking at our average bond energy for that particular bond. And so we'll kind of leave with that thought. And so again, right, you have these standard charts. We tend to be, like I said, in kilojoules. But again, you can look at other charts and might find other bond energies and other units of measurement. And so just watch the scale appropriately. And again, we'll come back to this, but you can already get a sense of the strength of bonds. So, right, a single bond is weaker than a triple bond, that sort of thing. And so you can kind of compare bond strengths. Silicon oxygen, pretty strong bonds. And something else to kind of just note, so oxygen is a pretty good thermodynamic sink for elements. So I think I've said that a few times in here that, right, a lot of our metals are found as oxides, so very common. And so that's also thermodynamically favorable as well, and you can just see that in the bond strength. All right, so we'll stop there on that note then. But we'll continue kind of quantifying that on Thursday and any other questions. And again, I apologize for the stream. I think we captured everything. I don't know if anybody's still alive, but all the information should be there, so I'll stop this.